Hi students, this is Asma Mushtaq from the EEVIBES, and in this video lecture I am going to explain how many methods are here for biasing a transistor. Why we actually bias the transistor? The purpose of biasing the transistor is to establish an appropriate Q point on a DC load line so that we can use it as an amplifier in an active region. So biasing actually establishes the Q point, which is also called the operating point of the transistor. Fine. The different biasing methods that are available for biasing the transistors are voltage divider bias, emitter bias, base bias, and then the last one is the collector feedback bias. And we will see in the coming lectures the voltage divider bias is the most widely used method. Fine. In the voltage divider bias, the voltages at the base terminal of the transistor, which is mentioned or referenced or marked as VB, are actually divided by using the voltage divider using the two transistors R1, resistors R1 and R2, uh, and the source voltages are VCC that are connected at the collector terminal as well. So a single voltage source is used for biasing the or for developing the voltages at the base terminal. All right. Now, the voltages at the base terminal can be determined by using the voltage division rule. Fine. But before that, when you will see this is certain point A, and at the certain point A, the current will have two paths. Either it can go through the transistor and wire resistor Re to the ground, or it can go through the resistor R2. Fine. So let's call it I1 and this is I2. In order to reduce the loading effect of the transistor, I will make sure the current I1 should be very large as compared to I2, or in other words, I2 is negligibly 0 or approximately equal to 0. This condition can be met when we will make sure that the R in base, which is the resistor over here, R in base is very large as compared to R2. Then obviously the maximum current will take the low resistive path, so the maximum current will flow through the resistor R2, and hence we will be able to develop the voltages at the base terminal, and the loading effect of the transistor will be ignored. Fine. If this is the case, like R in base is very large as compared to R2, then the voltages developed at the base terminal will be marked as VB is equal to what? Let's apply the voltage division rule. So R2 divided by R1 plus R2 into the source voltages, which is VCC in this case. Hence, VB will be equal to this. We know that the base to emitter voltages can also be mentioned as the voltage difference between the base and at the emitter terminal. So VB minus VE. This implies that if VBE is equal to 0.7 volts, then you can substitute the values of VB in this expression. You have the value of VBE and you can determine the value of VE. So VE will be equal to VB minus VBE. After determining the value of the emitter voltages, we can determine the value of IE or the emitter current, because we know the value of the emitter resistance, we know the value of the voltages at the emitter terminal. So we can just apply the Ohm's law for determining the emitter current, which is IE is equal to VE over RE. Since IC is approximately equal to IE, hence we will also know the value of IC, and this is the well-known equation. IC is equal to beta times of IB. So IC, which is equal to beta DC of the transistor into IB. From here we can also determine the value of the base current. So IB is equal to IC over beta DC. All right. So we have the value of IC. If you look at this diagram, you can clearly see that here you will have the voltages which are marked as the collector voltages. So the collector voltages will be equal to VCC minus the voltage drop across this resistor, which is VRC voltages, and that can be determined by IC into RC. So VC will be equal to VCC minus IC into RC. Fine. So VC is equal to VCC minus IC into RC. And finally, the last voltages that are left to be determined are VCE, which is equal to the potential difference at the collector and at the emitter terminal. Fine. In this way, you have determined all the parameters of the transistor in the voltage divider bias, like you have the value of IB, you have the value of IC, and you have the value of IE. You know all the currents flowing through the circuit. Similarly, you know the value of VB, VC, VE, and ultimately you know the value of VCE as well. Fine. One thing that you must always remember, that in order to reduce or eliminate the loading effect of the transistor, we assumed that R in base of the transistor is very large as compared to R2, and that condition is if R in base is greater than or equal to 10 times of R2, then we can simply determine the base voltages just like we did previously. But if this criteria is not met, then what will happen? This was our original voltage divider bias, and here the transistor will introduce the loading effect, whose resistance is given as R in base. So this is R1, here is R2, and here you are having the VCC. Now the voltage division rule simply becomes VB is equal to R2 parallel to R in base divided by R1 plus R2 parallel to R in base into VCC. And what's the value of R in base? That should be equal to VB over IB. Fine. So let's just do it. So R in base is VB over IB, and we know that IB is equal to IC over beta. So this become beta DC into VB divided by IE or IC. Both fronts are equal, that's why. Thank you for watching.